Okay, let's go and get started today. Happy, what's today? Wednesday. Happy Wednesday. And today we're going to be looking at kind of finishing up our look at synchronous communication, although we are going to have a couple more labs doing some stuff with it. But today we're going to look at what's called self-clocking signals or self-clocking synchronous communication. So let's go and get started. Now, as a reminder, when you're looking at synchronous communication, what makes it synchronous is it has a shared clock, meaning both the transmitter and receiver have access to a shared clock signal that they're both looking at, both using. And as we have done so far in the labs, that's been like a separate wire. We have this separate wire that acts as the clock channel, the transmitter, in the case of SPI or I2C, or even our synchronous thing that we did a few labs ago. That clock gets moved up and down by the transmitter, and the receiver looks at that and knows when to sample the line based on when those transitions happen. And there are a couple ways to share that clock signal. The one that we've looked at so far falls into this category 1, having a separate clock channel. In other words, we have this completely independent clock channel that in our case was a separate wire. Just like in SPI had SCK, just like I2C had SCL, and just like in our labs, we ran that extra wire from one of the boards to the other board, and that acted as the clock channel and only the clock channel. So in other words, in that separate clock channel setup, the clock is on its own channel, and it's completely independent from the data channel. But note that sometimes having a separate channel can be either difficult or inconvenient because we now have 2 wires instead of 1. And in the case of something like think of like a fiber optic communication link where you basically just have a light, and there's either light there or there's not light there, or wireless where you have a frequency and you can either put stuff into that frequency or not. But in those cases, there are cases where it's difficult or inconvenient or sometimes even impossible to have a completely independent clock channel. So the solution there is to somehow embed the clock signal within the data channel. In other words, the clock and the data are going to share that same channel in some way. And the question is, well, how's it possible? How's it possible to stick 2 different things, both the clock and the data, onto one channel? How do you do that? And we're going to look at a couple approaches to doing that today. This is not by all means an exhaustive presentation of every way you can have the clock and the data on the same channel, but we're going to look into a few of those today. Now, there are a couple approaches to this that we've already seen. We just didn't know that's what we had seen. For example, the clock uses a channel at some point in time, and then it switches over and becomes data at other points in time. And this is that is what's called anisynchronous synchronous communication. And actually, what we called asynchronous communication earlier, that's kind of what it did. It had a start bit that was a clock signal. That was a synchronization signal that during the clock or the start bit time period, it was acting as a clock synchronization signal. And then it switched to being data from that point on until the stop bit. And then the next clock signal was the next start bit. And so it was kind of switching back and forth, like synchronization pulse, data, 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 stop bit, synchronization pulse, data, 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 stop bit, synchronization pulse. So you could see it was that one channel switching from being clock pulses at one point, synchronization pulses at one point, to data for a while, back to clock, back to data, back to clock, back to data. And that's what anisynchronous means. It's like you have both the clock and the data on the line, but not at the same time. They're not combined. Now that brings us to the second approach, and that's to encode the clock signal at the same time as the data, and that's called isochronous. But the idea there is the clock and data are encoded in a special way that both are present simultaneously. In other words, the clock signal, you can think of it as the clock signal actually also carries the data, or you can think of it as the data signal also has the clock embedded within it. And those are often called self-clocking signals or self-clocking codes. And they're even with that, there's several ways to do that, and we're going to look at a few of those here coming up. All right, so self-clocking signals, the idea there is pretty straightforward. There are a lot of approaches to creating those. We're going to look at some of them today, including some that are kind of real world things. But the basic approach is to find a way that the clock and data can be combined into one signal. So you have one signal only, but inside that one signal, the clock and the data. You might still be thinking, well, that seems kind of mysterious. How do we do that? And the only real rule is we have to do that in a way that we can still extract the clock for its timing properties and also be able to recover the data from that combined signal. So we have to be able to kind of combine them together into one signal, and then on the other end, kind of pull them back apart again and say, okay, I know that this data is right, and I can see when the clock pulses are to know when the data is at each bit level or however it's encoding the data. And we're going to look at a few of those clock signal methods or self-clocking signal methods here, starting on the next slide. All right, so the first one we're going to look at is a pretty simple approach called pulse distance encoding. And essentially what pulse distance encoding does is the basic idea is if you have a square wave here, and it's either high part, low part, high part, low part, and what they've done is notice that's just like a clock. It ticks. Ticks high, ticks low. Goes high, goes low. So this looks a lot like just a normal clock signal, but you'll notice there's something kind of funky about it. And that is some of the low pulses are longer than other ones. So the way that that this is encoding the data along with that is if we have clock pulse and then the low pulse is very close to matching the same duration, that's a 0 bit. So in other words, if the ratio of high to low is about equal, that's a 0. But if I have a high pulse with a long low pulse, I count that as a logic bit 1. So looking at this looks like a clock signal just ticking away, but you'll notice that these two match, we get a 0. This one, the low pulse is longer than the high pulse, that's a 1. High pulse followed by long, 1. Short followed by short, 0. Short followed by short, there should be another thing going up there. That would be a 0. I should probably have drawn that edge going up there over on the side here, but you can imagine that. But the idea here is that we want to receive that by measuring the high part and then measuring the low part and then computing the ratio. And if it's closer to 1 than it is to 2 in this case, or 3 or whatever we set that to, then we say it's a 0. If it's closer to 2 than it is to 1, then we say it's a logic bit 1. And this is actually really pretty clever because it just is like a clock that's ticking. And notice that the time itself, how fast we're running this, doesn't matter. It's not time-based like with UART or with the asynchronous communication, because all we have to do is measure it for one cycle. How long was this high? How long is that low? Hey, they're about equal. It's a 0. The low part is longer than the high part and closer to being a ratio of 2. It's a 1. So we could run this really slow. This could be a second, or it could be a millisecond, and we can still get a 0 out of that, and we can still get a 1 out of that if this is 1 second, and that's 2 seconds, or 1 millisecond and 2 milliseconds. We could still get a 1 out of that. So notice it's not necessarily sensitive to timing, because it is the clock, but it also is the clock encoding the data in the ratio of high to low pulses. Very clever thing, and you can see how that's just one signal. Now, another version of that that is somewhat similar is called pulse length encoding. And pulse length encoding, it doesn't care about the ratio of the low to high. All it cares about is how wide are the high pulses. So if they're high for a short amount of time, 0. A longer amount of time is a 1. Now, note that in order for this to work, and again, this looks just like a clock. It's high, low, high, low, high, low. But what matters here is how long is it high. If it's a short duration, it's a 0. If it's a long duration, it's a 1. So how do we know what constitutes short and what constitutes long? Well, either the system itself has to be somewhat time sensitive, or in some cases you'll have systems that will have a preamble period or even a single bit that's always a 0 at the front. And then you know that how to use that to compare the rest of them too. So for example, if I always tack on a 0 bit at the beginning, and let's say this winds up being 1 millisecond, I know 1 millisecond is my yardstick. And if I have something close to that, it's a 0. If I have something close to twice that, it's a 1. So again, you can make this thing so it's not as time sensitive if you add that preamble. This one's a little bit more time sensitive than this previous one that we looked at here, but it still looks just like a clock, meaning it just goes high and low, but we're also encoding 0s and 1s in the length of those high parts. And there are a variety of those pulse coding schemes that we're not going to look at right now. I am going to look at a couple of real-world examples in just a second, but they're what's called differential pulse codes, which basically just measure the time of each of the pulses. And if we have a time that's the same as the previous one, it's a 0. If it's a time that's different than the previous one, then it's a 1. So in other words, as the ratio changes, if the ratio doubles, we get a 1. If the ratio halves, we get a 1. But if the ratio stays 1, we get the same bit that we had previously. And we're going to see a differential encoding scheme later on here today as well. You can also encode more than 1 bit for each pulse length, meaning that because you're not limited to a ratio of just a factor of 1 and 2, you could have 1, 2, 3, and 4. And now with 4 possibilities of pulse width ratios, you could encode 2 bits worth of information. So the first one could be a bit 0, 0, and the next one's 0, 1, and 1, 0, and 1, 1. And you can encode more than 1 bit at a time. And in fact, you could take that to extremes and encode a whole lot of information, including analog signals. And there actually are examples of how you could encode an analog signal using just a digital signal of pulses. And that's what, I don't know if you've ever seen hobby servos, but they're like little motors that have a little wheel on them that turn, that you used for RC aircraft that move the flaps and control the throttle and other things on aircraft, but they're also used in robotics and things like that. But those are actually controlled with a pulse width that can just change. So rather than just being ratio of 1 and 2, it can vary between a range of values, and that encodes an analog signal for where you want the motor to be. And we're going to actually take a look at that later today too. One place that the pulse coding is used is in infrared remote control. So if you have a television at home and it has an infrared remote control that you watch TV and change channels, and I don't know if you have direct TV or a smart TV or whatever, but if you have a remote control, chances are that it's an infrared remote control in some parts of its implementation. And or if you're in the labs at the university and you see the professor turn on the overhead projector thing that projects the computer screen onto the silver screen that's in the room, that has like an infrared remote control. Now, the way that those work is using one of these pulse coding methods. So here's an actual real signal specification for one of those. And you'll notice that it's using that first one that we looked at. In other words, look at the 0 bits here. They are always short, 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 short. But if I look at the 1 bits, they are short, long, short, long, short, long. And this is the entire message that when you press a key on your remote, this is the message that gets sent out. You'll notice that they have this logic 0 is a 562.5 microsecond pulse, followed by another 562.5 microsecond pulse. In other words, notice that ratio is 1 to 1. But if you look at what a logic 1 is, it's a 562.5 microseconds followed by 1.6875. So in other words, this number here is actually a ratio of 3. So 1 to 3. And so it's easy to sort those out. And if you look at the entire packet that gets sent, this is actually really easy to understand as well. They take the address, then they take the inverse of the address, and that's for error correction reasons, so you don't accidentally get things turning on or off. So make sure the address, and the address is how that thing is associated with the television itself. So each remote and each model and each brand, they'll give this thing an address. So when you press a button, it sends its address, and then the command is generally which button you pressed. And so there's the command and the logical inverse of the command. And then if this and that, the inverse of those match, and the inverse of this and that match. In other words, you XOR this with that, you get a 0. XOR that with that, you get a 0. Or no, you get all ones when you XOR those. But anyway, if this checks out as being correct, then the television turns on or changes the channel or does whatever command for what button you pressed was. And then this pulse at the beginning here, this 9 milliseconds followed by 4.5 milliseconds, that's kind of to wake the thing up and say, oh, this message is for me. I saw the right pulse length followed by the right space length. And now I'm going to start receiving the data. And when it gets to the end, it takes action. So if you actually had a little infrared transmitter, it would be really easy to write code on the Arduino that actually sent out these pulses that did things like turn on your TV. You just have to know what address your remote for your TV uses and what commands each button uses. And if you had an infrared receiver, you could hook an oscilloscope up and press these buttons and watch this stuff show up on the oscilloscope. It's a really cool thing, but notice it's using those pulses. Now, the other thing, there is one other reason why they're using these logical inverses, and that's because it makes it always take the same amount of time. So if I take this and its inverse, I can use that for error correction or error detecting. But I can also, that means that this is always going to be a long for a short over here. If I have a long over here, I'm going to get a short there. So this is always going to be 67 milliseconds for one press of the key to get into that message format. And it's not just NEC remotes. They were the ones that kind of created this format for their original television remotes. But there are a lot of other companies. I think Panasonic uses this, and Toshiba uses this, and Sony uses some form of this. But a lot of those remote controls use this kind of pulse coding, pulse length coding to do that. Now, I mentioned hobby servos earlier, and this isn't really a digital communication. This is analog, sort of. But I wanted to go ahead and mention that. But the idea there is the same way. That you have every 20 milliseconds, we have a pulse high for a period of time. And then 20 milliseconds later, another one. 20 milliseconds later, another one. And then what that happens is that pulse width can vary from 1 millisecond all the way up to 2 milliseconds. And if it's high for 1 millisecond, the motor moves all the way to one side. If it's at 1.5, it's in the middle. If it's at 2, it's all the way to one side. If it's at 1.6, it's at the middle, but a little bit over from that. And so you can vary this thing in an analog fashion, and the motor will track that position of the thing. Again, with the Arduino, very easy to implement something like this. Set the pin high, have a delay for a certain number of microseconds, and then set the pin low again. And if you hook that up to a servo, the servo control line, which is usually white, sometimes yellow, depending on the servo manufacturer, but you give this thing power and ground and the control signal, which is white, and output that from the Arduino, and you can now control that servo from one of the port pins on the Arduino. Very cool. And notice we're outputting that with the same kind of thing, that it's always 20 milliseconds between each pulse, so 20 milliseconds from there to there, and you can see those all line up. The only difference is how wide that high pulse is that determines the position of the motor. So it's a very clever way to communicate the position you want the motor to be in with just one single wire worth of data and have this wide range of 0 degrees to 180 degrees. And realistically, in practice, you can actually put in pulses that are shorter than 1 millisecond, like 0.5, and it'll be less than 0 degrees, or it'll be over here. And I usually think of 0 as straight up, and this would be like negative 90, negative 100, to positive 100. And some servos are multi-turn, so you can actually get them to turn multiple times, but they all use the same kind of control method for that. Okay, and that brings us to one of the more widely used forms of self-synchronizing or self-clocking signals, and that is a technique called Manchester encoding. And Manchester encoding was developed a long time ago for storing data on magnetic media, like magnetic tapes. And the way that it works is, well, before we do that, it's also widely used in Ethernet. So if you have a wired network connection or see the bundle of cables in the lab, or the lab's where the cables connected to routers that are available for students to plug into and use. Those Ethernet cords are using some sort of Manchester encoding to transfer the data. And also, Manchester encoding is used in some infrared remote controls. It's used in RFID tag applications. It's used for wireless, like communication for like Bluetooth uses Manchester encoding for the low level in some of the versions. Satellites, space probes, the hard drives themselves for how they store the data and encode the data to be stored on the magnetic platters have used this. Magnetic tape. There's just tons of things that have used this. And there are some advantages to this Manchester encoding method that we'll talk about here in a second. But the idea is pretty simple. That if you have a logic 0, it looks like this. High followed by a low. If you have a logic 1, it's low followed by a high. So they're just inversions of one another. So 0 is a... actually, I think I wrote that backwards there. Let me fix that. Okay, so let's look at encoding the letter A with Manchester encoding. So the letter A, which is capital A, is a 65. So we have a 1 in the 64's place and a 1 in the 1's place. So 64 plus 1, 65. So there's what my pattern looks like going across there. Now, and essentially all we do is when I have a 0, I plug in the pattern I have for 0. So high followed by low, high followed by low. When I have a 1, I plug in the pattern low followed by high. So here's a 0, high, low, 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 1, low, high. And so you notice that this looks just like a clock signal. It's high, it ticks low, ticks high, ticks low, high, low, and so forth. But it's also in varying a little bit how long it's high and how long it's low. Notice it's very uniform when I just have strings of zeros like this. But then when I have a 1, it's going to be a long pulse when I switch to a 1. And if I had a string of 1s, they would look very uniform, but I have a long pulse when it switches back to a 0. But that long pulse when it switches back to a 0 is going to be a long high pulse, like we see there. Now there is one problem though, and that is the line in this diagram was idling high. And we can't tell that the 0 started there because there's no transition. So there's no edge to detect right here at the beginning before that 0 pulse. So how do I know that this isn't the starting pulse here, and how do I know that that was a 0 there? Well, probably the easiest solution is to add an extra sync bit or sometimes a pattern at the beginning of the message called a preamble, which are just a few bits so that it can get synchronized. And one of the cool things about this is you'll notice that middle of every bit there's a transition. It doesn't matter if it's a 1 or a 0. It's the middle of every bit. The other cool thing about this relative to the kind of pulse distance encoding that we looked at earlier is that the length of a 1 and the length of a 0 are the same. It's the same width, no matter if it's a 0 or it's a 1, which can be useful. So the idea of what we're going to do with this Manchester encoding is we're going to add that extra bit at the beginning, and then we're going to look at how we would encode that and how we would decode that. So let's take a quick look at, there's the extra sync bit added, and it's added as a 1 in this case because the line idles high. If the line idled low, we would add it as a 0. But since the line idles high, we're putting it as 1 because we want to see this edge right here, this first edge. And that's going to start us off. Now, essentially what we're going to do is since that sync bit is always going to be a 1, we're always going to get that low pulse width right here. See this area right along the bottom of that first low pulse there. And we're going to use that as our time base T. And since we're always going to get that short low pulse, we'll always have the time base that we can then use to compare to the rest of these signals here to know whether they're short or long. In other words, with Manchester encoding, it doesn't necessarily matter how fast we go because we always can use this as our yardstick to measure these. So in other words, that first sync bit that looks like this is always going to be either followed by a 1-bit next or a 0-bit next as the start of the message. So let's take a quick look at those two possibilities. So those two possibilities, we have the first case where there's my sync bit, which has the green box around it. Notice that looks the same in both cases, but if I have a 0, notice how can I tell it's a 0? Well, here was the low pulse, and then the high pulse lasted 2 times the length of the low pulse. If that's the case, then it's opposite of a 1, so we know the next bit is a 0. And we end up at the middle of that 0 when I get done with measuring that high pulse. I'm up here, middle of the 0. And if I have a low pulse and then the high pulse matches the length of the low pulse, then I know the next bit has to be a 1. And I'm at the beginning of that 1. So if I'm at the beginning of that 1, I could then time over and wait until I'm at the middle, and then I could repeat that same process of measuring each of the lengths of the high pulse to know going from 1 to a 0, and each of the lengths of the low pulses to know if I'm going from a 0 to a 1. So we can just continue that process of looking at the pulse length that comes up next to determine the next bit value, and I can just keep doing that for all of the bits from that point on. Very clever, very cool thing. And notice the length of those pulses is always the same, so it's predictable. And you'll also notice I can always pick out that next pulse width as long as the signal is clean enough to be able to do that. All right, so encoding, sending, super easy to write the code for that, or develop the system for that. To send a 0, set the line high, delay, set the line low, delay. Again, maybe I should have put this picture, this picture on that page. And here, let me just do that real quick. I'm going to grab this thing, do a Control-C. We're going to go down a couple pages to here. I'm going to do a Control-V. I'm going to put that guy right there. Make it a little bigger. And we're back in business. All right, so again, send a 0, set the line high, delay for 1 time unit, set the line low, delay for 1 time unit. For a 1, it's just the opposite. Set the line low, delay for 1 unit, set the line high, delay for 1 unit. Very trivial code to write. I mean, you could write this in the for your Arduino in just a few lines of code in a couple of minutes. So a couple notes here. Each bit, no matter the value, takes 2 time units to send. You can see that right there. And also each bit contains an edge transition in the middle of the encoding. So after the first T, the line changes. And that's what makes this a self-clocking signal, is because that's kind of resynchronizing us for every bit, even though there's no specific clock signal, because the data has that edge in the middle of it. Very clever. Okay, so here's how the receiving works. Basically, we wait for that falling edge of the sync bit, and then we time that low pulse, and that becomes our yardstick to measure the rest of the signal by. That becomes T. We can then set the bit state to high because we know the start bit was always a 1. And then if the start bit state is high, then we basically just measure that next high pulse, and it's either going to be short or long. It's going to be closer to 2T or closer to 1T. If it's closer to 2T, we know the next thing is a 0, and we set our bit state to low. If we know it was 1T, then we set our value to 1 and leave the bit state high, leave it what it was. Or in other words, we could output high at that point. We would just output a 1 there. Now, there's a little bit of a difference here. There's something that's left out of this pseudocode just because it wouldn't fit. And that is, remember, we ended up at the beginning of the 1 here, where up here we ended up at the middle of the 0. So we need an extra thing, leave the bit state high, but then go 1 bit width, 1 pulse width to the middle of that 1. So we're in the middle of both of them here, ready to measure the next part. Now, if the bit state is low, we just do the opposite. If we get a long low pulse, it switches to 1. If it's a short low pulse, we keep it at 0 and output each of those things. And every 8 bits we get, we pop out the byte value. Now, that it might be easier for you to visualize as the state machine. And here's a little state machine that kind of shows that. So we are in the idle state. We get that falling edge of the sync bit. We end up in the middle of the 1, but we haven't output 1 yet. So we measured T though. And now we use that as a yardstick to determine short or long. So if I get a short high pulse, I go to the start of 1. When I get a short low pulse, I output that 1. So if I keep getting short, 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 and I was in 1, I keep getting 1s. Remember, it looks the same over and over. But if I see something where I now have a long pulse, and I'm in 1, I output a 0, and I'm in the middle of the 0. And if I get short, low, short, high, short, low, short, high, I keep getting 0s until I get a long, low pulse. So anytime I get a long pulse, it switches to the other bit. Anytime I get a short pulse, I'm staying the same bit. And you can see it outputting those. And with this, every 8 bits, I output a byte. And there's really no reason to go back to idle and resync like there was for the asynchronous code we did before. You could resync for each byte, but you don't have to, because as long as you just keep pushing the bits out there, have low, high, it's okay. Now, once we've stopped sending, we would need to go back and didn't get any pulse for a certain amount of time. Then we would reset back to idle to wait for the next message. Notice that there's also a ability here that since we're measuring these short pulses and these long pulses, that we could actually fine-tune T or have T slightly change over time. So rather than just being stuck to that first measurement, every time we have a short pulse, that's what T is. So we could actually average those or something like that, or use the last short pulse I saw as my new yardstick for measuring, so it can kind of tune itself as it's running. But you'll notice that there's no blind timing like there was with our asynchronous communication with the serial data units. It's not like just quietly sitting there measuring off, okay, a time unit has passed, sample the line. Time unit has passed, sample the line. It's always looking for the edges because it's looking at the pulse widths. And that's what keeps it synchronized for each of those bits. Very cool technique used all over the place. Okay, there's one final technique, keeping consistent with my one more thing mantra, and that is differential Manchester encoding. And this one it kind of works the same as Manchester encoding, but rather than having it be based on the pattern, is it low, high, or high, low, meaning 1s or 0, it looks for at the between 2 cycles. And if there's space between 2 cycles, if a cycle was the same as the one before, we get a 0. If it was the opposite of the one before, we get a 1. So here's that same message outputting that letter A, but you'll notice the waveform looks different now. So in the next cycle, so this is my preamble bit, or my sync bit. And then the next one, okay, this is the same as that one. So we put a 0. And we look at the next one. This one is the opposite of the previous one. We get a 1. The next one is the same as the previous one, 0. Same, 0. Same, 0. Same, 0. Same, 0. Opposite, 1. So in other words, anytime I see that long pulse, that outputs a 1. If I just see short pulses, I get 0. So you notice short, 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 short. Oh, there's a long low pulse, that's a 1. And so it's differential in that it's the difference between one pulse and the next one that matters, not which of those forms it meets. And the differential Manchester encoding has this really cool feature as well, that if the signal is inverted, then it still works, and you get the same set of, you don't get an inverted signal. You don't get 1s turn to 0s and 0s turn to 1s, because all that matters is, are they the same or different? So if this was inverted, this would idle low. This would be the inverse of that, but we'd still get that, and they'd still be the same. They'd just be upside down, and we'd still get a 0. So we'd still get the same sequence of bits out of that. We still get the same 65 out of it, whether the signal's inverted or not. So this differential Manchester encoding is used on some industrial and automation kind of networks to communicate information. A lot of other places it gets used as well. It gets used in some wireless things. But it's a very cool technique. And Manchester encoding is a really simple to implement but very robust. And one of the advantages of it is that notice that those edges always wind up in the middle of those pulses. So if you were to time off every pulse, we see an edge. And that can be an advantage because it makes the frequency band at which that communication runs in very consistent no matter what data you're sending. And that allows the system to, the physical properties of the system to be tuned for whatever frequency it's running at. And that's where you get things like Ethernet that work using this, using twisted pair cables, and you design the cables in such a way that the frequency that the Ethernet encoding runs at can reject a whole lot of interference that comes from the outside world because it runs at a consistent, steady frequency like this. So Manchester encoding, like I mentioned, also used on space probes that are out in deep space sending things back to us. It's a very useful thing. Now, we can layer other stuff on top of it, but Manchester encoding is a very powerful but simple method for self-clocking codes with a lot of nice properties. Okay, so that's it for today. Relatively short lecture. On purpose, I want to give you guys time to work on that lab with that wireless module, being able to read the registers from it. So work on that today. As always, if you have questions or problems or you need help, shoot me an email, give me a call, we'll set up a Zoom, and I'll do what I can to make sure to help with that. Other than that, stay safe, wash your hands, work on your lab, do it. There's going to be another one coming up. And we're actually eventually going to do a self-clocking code lab after we do the next wireless lab. So I actually might switch the order of those to give you a break from the wireless chip for a little bit. But work on that lab, get that done, and I'll see you guys soon.